Hello there, I'm just going to make a short video on implementing Euler's method for systems in Maple. Alright, so I've got this file posted in Blackboard for you to look at. So we're going to be looking at it, and remember we have the vector point of view versus the component point of view. Alright, we're going to be kind of more thinking about this as the right hand side being little f and little g as usual in the component form. Alright, this is the main thing you're going to want to make sure to copy over into any file that you're going to be wanting to execute Euler's method. You want to make sure you highlight and copy the Euler procedure over. That's the main thing to get over there. And notice what that inputs. The right hand side f and g function. T0 represents your initial t. X sub 0 is the initial x. Y sub 0 is the initial y value. H is the step size, and then t has to be inputted. That's the time you're approximating at. Just a quick word about what this does there. The eval f for these first couple things, it's just going to convert your initial x or y to a decimal number, rounding it to 30 decimal places, and in this case counts out the number of steps you need to get up to t. Alright, looking at the body of the loop, we're going to go from 1 to n, and what are you doing? Your next x value is taking your previous x plus delta t, or your step size. In this case we're calling it h, times the right hand side f. The next y value is the previous y plus the step size times g, as usual for Euler's method. Okay, the output of the procedure is an ordered pair. Alright, so in the document here, we're going to go through a specific example. Alright, now this one's a fully decoupled system, so we can solve it explicitly, and we'll let Maple do that later and compare, and then we'll go through a couple other examples. In this case, the initial t value is 0, the initial x is 1, the initial y is 3, the step size h, in this case, well, I'm writing it as delta t, that'll be h, and the Euler procedure is 0.1. Alright, so 1/10. Alright, the first thing we have to do is we have to define these right hand side functions. Alright, remember colon equals for defined, and then you're going to take the ordered pair, and to get the arrow to show up you're going to do a dash and then the greater than sign, and Maple will automatically turn that into the right arrow there. Alright, so execute both of these, so define the right hand side functions, and then we have to define a function that's going to send a generic t through the procedure to get an output value. Alright, to approximate it at that t value. So we're going to say t arrow over to the Euler procedure, which we have in our document. We also executed it, so it's working. We've defined f and g just previously. This is the initial t, initial x, initial y, and the step size. And notice we're putting in a generic t value. So this is a function of what I call the capital T. You could do lowercase t, doesn't really matter that part of it. Alright, now to check that this would work, I've done some test values here, and then let's keep kind of flowing through this. These next couple of things just show that in this case our step size is 0.1, so 1.4 and 1.5 are steps of size 0.1 away from 0. What happens? What does the procedure give you if you're not? What if you're between 1.4 and 1.5? It'll round it to the nearest step. So if we're at 1.43, it's going to round up to 1.4 and give us the same values what we had at 1.4. For 1.48, it'll round it up to 1.4 and give us those values. Alright, now how do we plot those? Alright, so we've got the solution. Maybe we want to graph it in the phase plane. I've got that done here. So we're going to use the sequence command. This E is outputting a bunch of ordered pairs, so we're getting a bunch of ordered pairs plotted in the phase plane. Okay, so you can copy and paste that code as needed there. You might need to change the number of steps. In this case it's 20 because we're going from 0 to 2, t equals 0, t equals 2, and steps of size 0.1. If you actually want to see the ordered pairs you're plotting, you can do that. Alright, so that's the group or the set of ordered pairs that are plotted up in this graph up here. Alright, now I've also defined in this document the x component and the y component approximations. You can do it using what I've called Euler x and Euler y below, but I've got a better way to do that I want to show you. So this all works. You can do it this way if you want to. Here's something which I just recently thought of how to do it. This I think is what I would suggest doing. E of t is an ordered pair. It's got two ordered pairs. So it's a list in Maple. If we go here and we put E of t and then put in brackets 1 afterwards, that's going to give us the first component out of that ordered pair. All right, so now let's look at what that does. We did E of 1.8 up above, and the first component was 26.6233. If I do xe, this is a function I called xe, which is going to send t, and then it's going to put through Euler's method, but only give us the first component, xe of 1.8. Notice the same value. Okay, so we can do the same thing for the y component approximation. You can either use this Euler y procedure, then the change in the Euler y procedure is only outputting the second component, or I think the slicker way to do it would be to define this new function, which I've just called ye. You can call it whatever you want, by sending it through Euler's method through the function capital E we've already defined, and now this time just give us the second component. So if we compare what we get with capital E by plugging in 3 in the second component, it's 52.348, etc. Now this function, if I put in 3, also gives us 52.348, etc. All right, so that's, I think, the best way to do that. All right, now what I want to do, and what the rest of this handout, sorry, not handout, what the rest of this file shows is how to compare that to the exact solution. So you can let D solve the initial value problem for us. So you got to type in the differential equations and then the initial conditions, and remember, you have to put the explicit dependence on T there. Now, by us doing that, it just tells us what the solution is. What we need to do, though, is to actually define a function if we wanted to, say, plot it or compare it to the approximation. So again, we're going to do x, I called it xe for x exact, and we're going to go t arrow over, so a dash and then a greater than sign. And what you want to do is just only copy the right hand side of what dsolve is telling us, paste that down below, and then execute it. Same for the y. All right, so now we've got new functions which we've called xe and ye. These are the exact solutions, and we're going to compare those to what I did up above, which were ye and xe, capital E's though. All right, so to compute the error, or we could actually now graph these things. So I've done that below here. So this first one, it plots the x approximate, okay, and we could have done it that way, all right, or we could have used the function I called x capital E there. All right, and the approximate x versus the exact x, and we've got that graph down below here. All right, and we could do the same thing with the y component. So if I want to compare the y component versus the approximate y component versus the exact, then we've got that graphed here. All right, notice these graphs have t on the horizontal versus y or x in the previous graph versus plotting it in the phase plane. All right, we can also plot the exact solutions if we want to in the phase plane. I've done that here, okay, and then I've compared that with the approximates. All right, now so again, we could plot that as a parametric curve. So this is in the phase plane versus graphing versus t. So this is x and y on the horizontal and vertical. That's graph as a parametric curve, and this is the plot of the approximates in the phase plane as well. We can see Euler's method's doing a decent job of approximating it. Okay, now to do the errors, say you wanted to get the error of the x component approximation at the endpoint, you can just type this in. All right, this is the syntax approach, eval f. This is telling us to approximate to 20 decimal places. Again, you could use the function I've called xa up above, or you could use what I called xe, and we'll get the same exact error. So again, you don't have to do the ya and xa if you don't want to. You can do these other ones. They'll give you the same exact errors, the same exact results. All right, so that's the Maple file, which I've called Euler Proc for Systems. All right, now I want to look at a couple other examples, and what I would like to do in this other file is I'm going to just show you how to go back through it. And the example I want to do, there's two of them. One's from the textbook, and one's from the handout that we went through in a previous class meeting, previous WebEx, and this was this partially decoupled system. All right, now just for time's sake, I think I'm going to stop this video and make a second one going through these two examples.